Lesson number 6. The learning objectives of this lesson are understanding percent mass of element in a molecule or compound and understanding limiting and access reagent. Percent mass of element in a molecule. It is actually the mass contribution of element in a whole molecule as in molecular mass. We know that if we have a molecule, let's say calcium carbonate. So calcium carbonate has its total mass, which is equivalent to 100 grams per mole, which is the molecular mass of this calcium carbonate. So what mass of calcium is there? That was 40. What mass of carbon was there? That was 12. And what mass of oxygen was there? That was 3 cross of 16. That was 48. So this mass of each element as 1 mole of each element, because we see that here in a carbonate where carbon is making double bond with oxygen, single bond with one oxygen and single bond with another oxygen, and it is having a negative charge on oxygen, and we have a calcium ion which is having a positive 2 charge, will be attracting the oxygen, and that makes a calcium carbonate. So each atom contributes to the mass of this molecule, this whole molecule. So what percentage of the mass of each element in the total mass of this molecule is actually the percent mass composition of the element in the whole mass of the molecule. So we will be finding out that. Let's take an example of sulfuric acid. And this we are going to find out that what is the percentage of hydrogen is there, sulfur is there, oxygen is there in sulfuric acid. So let's find out what is the whole mass of sulfuric acid. So mR of sulfuric acid. This is 2 cross of 1 plus 1 cross of 32 plus 4 cross of 16. We get 2 plus 32 plus 4 cross of 16, we get 98 grams per mole. That is the whole mass of sulfuric acid. So what is the percent mass of hydrogen? So percent mass mean that out of the total mass, the mass of hydrogen that is contributing to the total mass of sulfuric acid. So percent mass will be like this. So mass of hydrogen. So if we look over here, there are 2 atoms of hydrogen. If I draw the structure of sulfuric acid, this is sulfur making double bond with one oxygen, bond with another oxygen, single bond with one oxygen, and another single bond with one oxygen, which is making a bond with hydrogen or bond with hydrogen. So here we have 2 hydrogen, and each hydrogen has a mass of 1 gram. So 2 hydrogen means we have 2 grams. So 2 upon 98 cross 100. So out of this total 98, only 2 gram is hydrogen. So what percent does it contribute? So 2 upon 98 times 100, we get 2.04%. This is the percent mass of hydrogen in sulfuric acid. Now let's find out the percent mass of oxygen. How many oxygens are here? 1, 2, 3, and 4. This oxygen is 16, this oxygen is 16, this oxygen is 16, 16. Either you add 16, 16, and 16, or you simply multiply 4 by 16, and we get 64. So out of this 98 grams, 64 grams is oxygen. So 64 upon 98 times 100, what do we get? we get 65.3% mass of sulfuric acid is oxygen. Now let's find out the mass percentage of sulfur. We have only one sulfur atom here and its mass is 32 grams. So 32 divided by 98 cross 100. What do we get? We get 32.65%. If we add all the percentages together, what do we get? If we add them all together, we get 99.99%. This means that this is equivalent to 100% since we have written these values in 3 significant figures and this here is a 4 significant figure. So if we add the whole answer all together, we will end up with the 100%. This means that out of this 100%, 2.04% is hydrogen, 65.3% is oxygen, and 32.65% is sulfur. Why do we need to do this calculation, the percent mass calculation in a molecule? Is just to find out that what percentage of a particular element is there in a molecule. This could also be helpful in the medicines. For example, zinc is needed by our body as a supplement, and there are many compounds of zinc that is available over the bench, but there is only one substance, one compound of zinc which contains the same amount of zinc element that is needed by our body, that is somewhere 150 micrograms. So when we calculate this percent composition of each element in a molecular formula, we find out that what amount of that particular element is in there. There is another beautiful contribution of this percent mass in the chemistry is that when we have a percent mass or a percent of element, so we can find out the molecular formula as well. We will be doing this example later in this lesson, but first we need to look into that what is the beauty of this percent mass calculation. So let us find out what is the mass percent of carbon in glucose and a sugar molecule. This will give you a greater or deeper knowledge of why we do the percent mass, because in this we will be finding out a different mass percent of carbon in the two molecules. And the molecules also tells us that, you see, there are only 6 carbon and there is only 12 carbons. So this also tells us that the one which contains a bigger amount is going to have a bigger ratio. So let's find out what is the mass percent of this carbon in each of the molecules. So this molecule is a glucose molecule. This one is a glucose molecule. You must be familiar. And this is a sugar molecule, which is a disaccharide. So let's calculate. So first we need to find out the MR of glucose. C6H12O6. So 6 cross of 12 plus 12 cross of 1 plus 6 cross of 16. What do we have? We have 180 grams per mole. So mass percent of carbon, this is equals to, how many carbons are there? 6 carbon, and each carbon accounts for 12 grams. So 6 cross of 12, what mass is there? 72. 72 upon 180 cross 100, what do we get? This is 40%. It's in there. Now let's find out in a sugar molecule. H22O11. 12 cross of 12 plus 22 plus 11 cross of 16. What do we get? This is 342 grams per mole. So percent mass of carbon, this is equals to, we have 12 carbons, so 12 cross of 12, which is the mass of carbon, we have 144 upon 342 times 100. This is equals to 42.10 or 42.10%. So you see that there is a very minute difference in percentage of carbon in the two molecules. So percent mass theta tells us that what actual percent of that particular element is present in a molecule. Before that, I make a remark, I make a statement that we can make sure just by looking at the molecular formula that the mass is in the sugar, it should be higher in case of carbon. But upon calculation, what we found out that the case is not that evident, because 40 and 42 is not a big difference. So without prior calculation using the proper methods and units, you can't make a quick judgment. So that will be a life lesson, that you shouldn't be a judgmental until and unless you have a thorough inspect into that. So we have a thorough inspect right now here, and we look into that what is the mass percent of carbon in each of the molecule, and we come up with the answer that it is 40% in case of in glucose and 42 in case of sugar. But when people get a disease, you must be familiar about this, a jaundice, basically glucose is provided or given to those patients rather than sugar. And why is that? That could be a very good question to look into, since both of them, they are providing the same mass of carbon in there. So why do we need to use glucose rather than sugar? So you need to look into that, and I'll be happy to hear your comments about why we need to use glucose rather than sugar. Now let's move on. In order to calculate the mass percent of nitrogen in 3.50 gram of calcium nitrate, again, this is a very basic question. First, we need to calculate the MR of calcium nitrate. Calcium is 40 cross 1 plus, since there are two of the nitrate ions, so 2 times mass of nitrogen is 14 cross 1 plus 3 cross of 16. What do we get? The answer is 164 grams per mole. We need to find out about nitrogen. So percent mass of nitrogen, this is equals to how many nitrogens are there. You see, if I draw the molecular formula of this, nitrogen is making double bond with one oxygen, another double bond with another oxygen, and a single bond with oxygen, which is making a negative charge, which is having a negative charge. There is another nitrogen molecule making double bond oxygen, double bond with oxygen, and this with a negative charge, both of them making an ionic interaction with the calcium ions. So you see that in this whole molecule there are 2 nitrogen atoms. So this means that 2 cross of 14, that is 28 upon 164 times 100. What do we get? we get 17.07% of nitrogen in there. So this is how you calculate the percent mass of element in a molecular formula or in a compound. Now let's talk about the limiting and access reagent, which is the second objective of this lesson number 6. So first we need to understand what is limiting and access reagent. First we will be talking about limiting reagent. So a reactant molecule that limits the amount of product produced is known as limiting reagent. This one is known as limiting reagent because limit means that it is holding back the amount of product to be produced. So if that substance is either in a small amount, and yes, definitely it should be in a small amount, that is why it is producing the limited amount of the product. So the one which is producing or holding back the amount of product or controlling the amount of product to be produced is the one that is the limiting reagent. And then we have the access reagent. So access reagent is the reactant present in access amount, that is known as access reagent. Now how do we find out that the particular reagent is in access? For this we must do some calculations in order to find out that which one of them is a limiting reagent, and if that limiting reagent is limiting the amount of the product, this means that the other substance could be the one which is in access. So that becomes an access reagent. So looking at the equation, like we have an equation in which nitrogen reacting with 3 moles of hydrogen and it is producing 2 moles of ammonia. And these two are the reactant molecules. This is reactant number 1 and this is reactant number 2. So just by looking at the balanced chemical equations, you can't say that which one of them is the limiting reagent or which one of them is an access reagent. For this you must do some calculations. There must be some actual amount of the substance that has been reacted and which are not taken as in the same ratio as the balanced chemical equation actually works. So this will give us an insight about which one of them is the limiting reagent. So let's do some calculations first. In the first example problem, you have 500 ml of each of nitrogen and hydrogen react to produce ammonia. So which one of them is limiting the yield of ammonia? So we are provided with 500 ml of nitrogen and 500 ml of hydrogen. And we need to find out that what amount of ammonia they are going to produce, and from that we will be finding out that which one of them is limiting the production of ammonia. So let's find out. Since they have given us the 500 ml, this means that we need to convert it into number of moles. That is the necessary evil because we are dealing with the balanced chemical equation. So nitrogen reacting with 3 mole equivalents of hydrogen, it will produce 2 mole equivalents of ammonia. So 500 ml into number of moles, we have a very beautiful relationship, and that relationship tells us that we have a given volume here, we have number of moles here, and we have a volume at RTP or STP. Volume at STP or RTP. So we are very well familiar about this. So volume at STP is 22.4 dm cube or 22,400 cm cube, and volume at RTP is 24 dm cube, or you can say that this is 24,000 cm cube. So dm cube or liters, cm cubes or ml, like we have cm cube or ml, we can use any kind of. So let's find out, let's look at this reaction happening at room temperature and pressure. So let's find out that what number of moles are there. So number of moles, since this is the subject, this means that volume upon the volume at RTP will be the area that we will be working on. So 500 upon 24,000, what do we get? This is 0.021 mole. This number of moles of each of nitrogen and hydrogen is given, and they are reacted to produce ammonia. So let's find out which one of them has produced which substance, which amount of ammonia in this reaction. So a ratio in case of nitrogen. Let's make nitrogen a subject here. So nitrogen ratio ammonia. 1 mole is producing 2 moles. So 0.021 will produce how much? X. This tells that X is equals to 0.021 cross 2. And what will be the amount? This is 0.042 moles. Can we find out its volume? Simply multiply it by the volume at RTP. So 0.042 times 24,000. What do we get? We get 1,008 ml of ammonia that is being produced. Let's find out for hydrogen. So hydrogen ratio ammonia 3:2. This information, this is coming from the balanced chemical equation, as this sets a scale. So 0.021 will produce how much? That is X. This implies that X is equals to 0.021 cross 2 upon 3. So what do we get? The X is equals to 0.014. So volume will be 0.014 times 24,000. We get 336 ml. So you can see that we have an equal amount of both these reactants, equal amount of nitrogen and hydrogen, and we can't make or complement before digging into the calculations that which one of them is the limiting reagent. So for this we need to do some calculations, and we come up with the idea that if we take 0.021 moles of nitrogen, it will be producing 1,008 mLs of ammonia. But if we take the same number of moles of hydrogen along with nitrogen, it will be producing 336 ml of ammonia. So actually, which amount of ammonia would be produced? So the one which is producing the lowest amount of ammonia is the one that is limiting the production of ammonia and is yielding the limited or minimum amount of ammonia. So here, nitrogen, hydrogen. Here, hydrogen is the culprit, which is actually the limiting reagent. It is limiting the amount of ammonia being produced at the end of the reaction. So this is the limiting reagent. Now, relating it with the percent yield. So percent yield is again come up in an action in order to find out what amount of ammonia is being produced. So when we have a limiting reagent, this is producing a limited amount of ammonia. But then they give us that there is a yield of ammonia, which is the actual yield, 295 ml of ammonia. This is actually the actual yield. In example problem number 2, it was seen that 295 ml of ammonia has been produced in actual experiment. So what is the percent yield of ammonia? So let us make ourselves clear that limiting reagent is not the one which is decreasing the actual yield. Actual yield has its own factors which are limiting the amount of substance to be produced. The limiting reagent that we found out through the calculations is the one which gives us an insight that if we take an equal ratios of the reactants, then which one of them is going to limit the product. So we just do it on the paper to find out that which one of them is going to limit the product formation. So why not to take it into an access amount to receive more product rather than limit the product. So this is the aspect of finding out the limiting reagent. And sometimes when we actually perform a reaction and we see what amount of the product is obtained and we root back it into the amount of the substance we have taken, so we also found out that which one of them we have taken in a small amount, so we simply add it into the reaction mixture to make it at large to provide more product at the end. So actual yield is something which is affected by the conditions, by the process, which is limiting the amount of substance to be produced. So there is a little difference in the two. So first, you are quite familiar how to find the percent yield. So percent yield will be 295, which is the actual yield, upon the theoretical yield, which is actually the yield which we have calculated as the yield which is going to be the limited one. So 295 upon 336 cross 100, we get 87.79, and you can say that this is somewhere 88%. 88% of the substance we have received at the end of the experiment, which is the actual experiment. And the third example problem, identify the access reagent. In example problem number 1, calculate what amount of access reagent is required to produce ammonia limited by limiting reagent. Okay, first we need to identify the access reagent. If you look over here, the one which is producing a greater amount of ammonia is the one which is actually present in a large amount. And why and how? Because the other substance which was taken in this very same amount, but it has limited the production of ammonia. This means that the other substance which was actually in the same amount with the second substance, but since second substance produced a small amount of ammonia, this means that a very small amount of the first substance has been used. So this means that nitrogen here is in excess amount. So this one here, nitrogen here is in excess, because a very small amount of this nitrogen is being used to produce the ammonia. So here we make our statement that nitrogen is an excess reagent. A lot of it is left as leftover, or you can say that unreacted. It is leftover or unreacted. The next part of this example problem is to calculate what amount of excess reagent is required to produce ammonia limited by limiting reagent. This means that the limited amount of ammonia is being produced. So for that limited amount of ammonia, what amount of nitrogen is we need? This comes from calculation again. We need to find out that for that limited amount of ammonia, how much of nitrogen do we need? So we will be referring to example problem again. Number 1 again, that we had 0.042 moles of ammonia that were being 0.014 moles of ammonia that has been produced, which is the limited amount of ammonia. And for that limited amount of ammonia, what number of moles of nitrogen are required? So we need to find out that. Let's do some calculation. So again, we are going to do the ratio nitrogen ratio ammonia. Equation tells us that 1 mole produces 2 moles. So for that limited number of moles of ammonia, 0.014, which is the amount of ammonia which is being produced by the hydrogen, which is limiting the production of ammonia. So for this many number of moles of ammonia, how much of the nitrogen is required? That is X. So X is equals to 0.014 upon 2. We get 0.007 moles of nitrogen. So this many moles of nitrogen do we require? So let's find out into the volume. So volume of nitrogen, this is equals to 0.007 moles times 24,000. What do we get? This is equals to 168 ml. So if we take 168 ml of nitrogen and we take 500 ml of hydrogen, it will produce 336 ml of nitrogen, ammonia. So you see that these things, they are not in a ratio that is we can see in the balanced chemical equation. So for whenever you do calculations, you're not supposed to take mLs or grams into ratios. You must convert them into number of moles to work it into ratio, because in a ratio method we must have a scale and we must have the substance to figure out. So for this we must convert these mLs into the moles in order to find the right answer. And you see that how they are limiting each other and what amount of the excess reagent is actually needed to produce that limiting amount. And we can also find out that how much extra nitrogen we have taken. So 500 minus 168, we get 332 ml. So we have taken 332 ml extra, which could be wasted, which could cost us, and that could be a bad or negative impact if we are performing this experiment and using this experiment or reaction on the industrial scale. So in industries, we work out the balanced chemical equation to find out that what amount of each substance we should use to produce a product of demand. Like for example, sometimes company asks for like 5 gallons of ammonia. So for those 5 gallons of ammonia, how much of nitrogen and hydrogen is required? So we first do the calculation, and then we set our experiment, and then we produce 5 gallons of ammonia. So this is how industries works. So thank you for today.